I'm Drew Weisserman, and I'm going to be teaching you about MCMC and how it works. So just a quick note before we begin. This video is mostly intended to teach you about the math and ideas behind MCMC. The demo, provided alongside this presentation, will give you a little more in-depth look as to the actual Python implementation of MCMC and how to use it in Python. This guide is mostly intended to get you to understand the math behind it and understand how they work at a fundamental level. That said, I think understanding how it works is something you need to do before using it, so let's jump right in. Say we're in a situation where we have a model we want to fit to data. We have a set of data points, and we know what form the model takes, say a quadratic model, but we don't know what parameters of the model fit the data best, say the a, b, and c in the quadratic function y equals ax squared plus bx plus c. So how do we estimate those parameters? There are a whole bunch of ways to do this, but we're going to focus on a form called Markov chain Monte Carlo fitting, also called MCMC fitting. The Python module MCMC is a Python version of this method. Let's go ahead and talk about how it works. So let's start with an analogy. Imagine you're in the dark in a foggy hill. The hill is bumpy and the fog is thick, so you can only see right around you. The goal is to reach the top of the hill, or at least reach the highest point you can, so you can get above the fog, but you don't know where that is. So how do you find the highest point you can? So maybe you take a look at the ground right around you and you figure out, what direction will take you the highest for each step. And then you walk in that direction, and after you take a step, you check again, see which direction will take you the highest, and keep repeating over and over. They'll probably take you higher than where you are right now, which is a good thing. But then you run into a problem. What if you reach a local maxima, a little peak that's still not the highest point? Then you're going to look around, you're going to say, okay, the single step that'll get me the closest, or the highest up, is to not move at all. But you can get higher than where you are. So maybe you look around and you decide that every once in a while you'll take a step downward. Not often, but often enough that you can take a step down off from that local maxima and continue wandering around, and hopefully the next hill over is a good spot. But maybe that's still not the global maximum. Maybe that's still not the best spot. So you pick another idea that might help. So say you do that whole path, you try going up once, eventually taking, steps down, but eventually you'll settle into a peak. Then you go back to your starting location. Then you repeat the process, starting off another direction or a few steps over, so you reach a different local maxima. And then you do that again and again, a whole bunch of times. And hopefully those locations will get you into different spots, and hopefully one of those locations will get you above the fog. That's how Markov chain Monte Carlo fits, or MCMC fits, work. The Markov chain, part of the name, means that you will randomly pick a direction to go in, and you'll occasionally take a step downwards. Whereas the Monte Carlo part of the name means you'll do this process a whole bunch of times, seeing where all of those paths go in the aggregate, rather than just doing it once. So now let's drop the analogy and go more into detail as to how it works. Let's start without getting into too much math, because math isn't too necessary to use MCMC fits, and because math is really complex. So MCMC fits use what are called walkers. So just like the person trying to get through the fog from before, a walker is a list of positions that your model explores, starting at whatever spots you decide. Typically, you'll begin them all really close to one another. You'll usually have dozens or hundreds of walkers, depending on how many parameters you're trying to fit for. At each step of time, or time step, these walkers pick a random position around them in parameter space. How they pick a position around them depends on the exact implementation of your fit, but for now, it suffices to say they just pick a random spot. Then, each walker checks how much better a fit that location is, done by calculating what's called the log likelihood. Essentially, the logarithm of the likelihood that your model will spit out the observed data. And we'll get into that more in a minute. And because we're using a logarithm here, a higher log likelihood means that our model is more likely to spit out the observed data, essentially meaning our data is a better fit to the model. If the log likelihood at the new spot that it finds is a better fit than its current location, the walker will always, without fail, move to that new spot. If the new spot is a worse fit, then it'll have a random chance of moving to the new location, depending on how much worse the fit is. So if the fit is only a tiny bit worse at the new location, there's still a good chance that the walker will move there. But if the fit is a lot worse, there's only a really, really small chance the walker will move there. And once you've done that for all your walkers, you finish a time step. You then repeat that process for a long time, typically hundreds, thousands, or even millions of time steps, until the fit is finished, and we'll go into that in more detail later. Then, the total path each walker takes is called a chain, and at the end of each fit, you should have dozens to hundreds of those chains that you can go ahead and compare. So that's all well and good, but we mentioned something called a log likelihood before. What is that? So all of these sorts of fits, like Markov chain Monte Carlo methods, are based off of Bayesian statistics, which, without getting too in-depth, means you're working with probabilities rather than discrete values. That's annoying to physically have to figure out the math behind, but it really works well when you're wanting to find the potential probability distribution of these parameters, which we are here. So all of Bayesian statistics is based off of Bayes' rule, which is given right here. Given P of H given D, so the probability of event H given event D, we already know what's happening, is equal to this right here. It's equal to the reverse, P of D given H, times P of H divided by P of D. So in this case, we can say that our two events are H, meaning the probability of our likelihood being the true model, and event D is the event of our data being the data we observe. So then P of H over D is called the posterior probability. This is the probability of the model given our data. So whatever maximizes this is the most likely model given our data, which is good. That's the value we want to maximize. We want to maximize the posterior. P of D given H is the reverse. It's called the likelihood. It's the probability of the data appearing given our model. So it's how well the model fits the data. And you might think, oh, well, we just want to maximize how well the model fits the data. But not necessarily so in our case. Because of P of H, the probability of our model existing in the first place are prior. So how likely our model is in the first place. So if you have a model that fits your data a tiny bit better, but you really don't think that that model is likely to occur in reality, then you're less likely to believe it, right? You're more likely to pick a model that makes physical sense, even if it fits the data a tiny bit worse. And so that's what the prior is there to indicate. It's how likely your model is in the first place before you start looking at any data. P of D, meanwhile, is the evidence, the probability of your data occurring, but we can ignore this one because for most applications of this method, your data is going to be the same, right? You're comparing your different models to the same data, and so P of D is a constant value. Since we just want to maximize this, we can just kind of ignore it, meaning we want to maximize just the multiplication of the likelihood and the prior. So let's take a look at log likelihoods first. So first, we convert this into a logarithm. So we use logarithms, like I mentioned earlier, for two reasons. One, these values we're working with, these likelihoods, can get really, really small when you're working with a lot of parameters, to the point where computers can have trouble working with them well if we're not careful. A logarithm turns the likelihood of 10 to the power of negative 10, that is 0.00000000001, just to negative 10, which is a lot easier to do math on. And a value that has a higher likelihood has a higher log likelihood too, so maximizing one maximizes the other and gives you the same location parameter space. Secondly, and more importantly, the reason we use logarithms is that the logarithm of two values multiplied by each other is just the sum of the logarithm of each one separately. So the logarithm of a times b is logarithm of a plus the logarithm of b. Or in this case, if the posterior is likelihood times the prior, then the log of the posterior is just the log of the likelihood plus the log of the prior. So we can just find those two values separately. So if we can calculate the log likelihood and the log prior of our set of parameters, we can calculate our log posterior. So let's look at log likelihood first. We can talk about our log likelihood as log of the probability of our data given our model. But our data is a lot of different individual data points, right? Dozens or hundreds of them as usual. So we can multiply the probability of each individual data point to get our likelihood. So given your n data points d1, d2, d3, and so on, the probability of your data given the model is the probability of data point 1 given your model times the probability of data point 2 given your model plus the probability of data point 3 given your model, and so on. And remembering how logarithms work, that just means that the log of your likelihood is a log of the probability of your first data point given your model plus the log of the probability of your second data point given your model, and so on. So you can just do a sum of those individual log probabilities. Typically, to define this, or to actually calculate those individual values, we use what's called a chi-squared log likelihood, given by right here. the log likelihood is negative 1/2 times the sum of the difference between your expected data points given your model and your actual data points squared over the error in those data points squared. So if you minimize the difference between the model's estimate of the data value at a given point and the actual data value at that point, you increase the log likelihood. But if you're wrong, it doesn't punish being wrong as harshly if the error is higher. Being off by 1 unit from the actual data when the error is 10 units isn't as bad as being off by 1 unit when the error is 0.1 units. Now, what about priors? How do we calculate these and how do we implement them? So, without getting too much into the math, a prior probability represents what is originally believed before new evidence is introduced, before your data is introduced. Well, a posterior probability takes this new information, the data, into account. So this prior probability, this prior belief, can take different forms. It can take, for example, priors derived from earlier work on similar data, or priors derived from what is physically possible. So to take an example of the first one, so priors derived from prior studies. Say you were writing a paper about studying a fake planetary system. An older paper you read studied a planet in the system and found it had a period of 10 plus or minus 0.1 days. But you have new data you're working with, or you're using a different method of finding the period or something, and you want to find that period again. In that case, it might be helpful to assign a Gaussian prior to this planet's period of the values the paper found, with a mean of 10 days and the standard deviation of 0.1 days, which are what they found earlier. And so what a Gaussian prior means is you believe that the parameter distribution should follow a Gaussian distribution, or your original belief is that that parameter distribution follows that Gaussian distribution. And so that means that even if a period of 50 days fits the data a tiny bit better than a period of 10 days, you're more likely to select the period of 10 days because your prior means you need a lot of evidence to take a value of 50 days as true. To take another example of priors being derived from what's physically possible, say you're trying to fit for the mass of this planet. You know that the planet has to have a mass of larger than 0, obviously. It has to have a mass of, say, less than 1,000 Earth masses, because a planet that large would disrupt the other planets in the system in a way you're definitely not seeing. But you really have no idea what the mass might be between those two values, right? You have no reason to prefer the code spitting out 1 Earth mass to the code spitting out 999 Earth masses. In that case, you might want what's called an uninformative prior, one that doesn't really give you much data, give you much data or give you any bias on the results. So in that case, a uniform prior might be appropriate, right? Because you would uniformly believe the result being anywhere between 0 and 1,000 Earth masses. And that also means that you would have a probability of 0 outside that range, meaning your fit will never find a probability below 0 or above 1,000 Earth masses. No matter what happens, you will not believe that the mass is outside those values. And that's what a prior is. It represents your original belief state before you look at the data. Just as a technical term, by the way, a prior is what's called informative if it expresses specific, definite information about a parameter. An informative prior is more strongly informative if that information constrains parameter space more strongly. For example, a Gaussian prior in the period we mentioned earlier is more strongly informative if it had a standard deviation of 0.1 days, and more weakly informative if it had a standard deviation of 1,000 days. Uninformative priors are the extreme there. They express very vague or general information about a parameter, often simply limiting that parameter to what values are physically possible. So something like the mass of this planet must be above 0 is uninformative. So say you've got your prior and your posterior for whatever you're trying to fit written as Python functions. And you got your MCMC running. But it's been running for a while. How do you know if it finished? And how do you visualize the results? So, in short, in general, a fit is finished if the chains you're fitting are converged. Converged in this case means that they all follow a similar distribution by the end, and they've satisfactorily explored parameter space in a way that makes you confident they follow the true best fit distribution. Now, that's kind of a vague definition, and that's intentional, because it isn't possible to guarantee convergence in a mathematical sense for anything more complex and like fitting in line, and so there's not really much point to me explaining the official mathematical definition behind it. So, as a result, any argument you make is going to be sort of informal. We can still show to the best of our ability that these chains are converged. So, the most common and easiest way to do this is to look at how the chains evolve over time. So here, I've included a sample plot showing the distribution of chains for each variable of the fit we're going to be using in our demo. The exact variables don't matter, but each of these rows represent a single variable. As you can see, the chains all start out at some given point and quickly expand into a distribution, exploring parameter space, and settle in what we know to be their best fit distribution. And that's good. We can go ahead and quantify this by calculating what's called the autocorrelation time. Well, I'm not going to get into the math behind it. Remember that each step in a chain has to be pretty close to the one before it because it only looks in a small area around it. And so the autocorrelation time is, for a given parameter, is the amount of time it takes before the chain forgets where it started, basically. So if you run it for enough autocorrelation times, then it doesn't matter where you start your fit, it will eventually reach the best fit distribution, even if it's going to be very, very slow at doing so. Typically, you want to run your fit for at least 50 times the autocorrelation time for each parameter. So find whatever the highest autocorrelation time for a given parameter is, and run your code for 50 times. Or keep running your code until the autocorrelation time is 1/50th the time you've run it. In addition, when you're getting your samples, so at each walker at each step, it helps to do two different things to better understand your data. The first is called removing the burden. And to think about this, we can see that, say for this parameter right here, we know the best fit distribution is this very tightly constrained value right here, right? But if we just, take a look at the average of all the parameters, or of all these steps of each chain, we're going to include this whole bit right here, which we don't care about. So removing the burden is basically just getting rid of all the steps of each chain before they arrive at the actual parameter distributions. And that prevents your initial walker positions from influencing your results. So typically I like to remove a couple autocorrelation times. I use 5 just from the start of your walkers, or start of your chains. The second thing to help is doing what's called thinning. So like I said earlier, it takes about 1 autocorrelation time for a walker to forget its previous location. So when checking out your total distribution, this whole set right here, you only take a look at 1 step each autocorrelation time for each walker to make sure the values you're getting are not correlated, to make sure that they're truly independent of each other and they're not influenced by each other. And so once you have that, you can just go ahead and take each walker, take each autocorrelation time step of each walker, and flatten them all out and just look at the distribution of those values over the remaining part of the chain. And that should give you a good substitution for the best fit parameter distribution of each parameter. Finally, you can visualize your results here using what's called a corner plot, which looks like this. It shows the distribution for each parameter along the diagonal, as well as a 2D distribution for each pair of parameters, which lets you visualize any correlation between parameters. So like right here, we can see there's a very positive correlation between these two parameters here, and a rather negative one between these two right here. Note that having correlations isn't a bad thing. Often you can substitute one parameter for another and have it mimic the data pretty well. But it is something to take note of. So yeah, once you've run this fit for long enough and once you visualize your results, you're ultimately done with your MCMC fit. And that should be all you need to do for your MCMC fits. So like I said, the demo should provide a in-depth explanation as to how to physically use the Python implementation of this, but I do hope that this presentation was very helpful in helping you understand how MCMC fits work in the first place. Thank you.